In this lesson, we will cover exponent rules and how they relate to scientific notation. First, one application of exponents is that they can express very large numbers in a concise way. For example, a very large number is something like 100 billion. So a 1 followed by 11 zeros. This thing here. Large number takes a long time to write. You could also write this as 10 to the power of 11, where here the exponent 11 tells you how many zeros there are after the 1, essentially saying how many times did you multiply by 10. This is much shorter to write than this, so in some cases, this might be preferable. Also, you could express very small numbers not by multiplying by 10, but by dividing by 10. So for example, 1 divided by 10 to the power of 5. This is 0.00001. So this is a very small number, but here we are using exponents to express it. Now, why be concerned with large or small numbers? It's that they show up in the real world, and here I've included a couple of examples of those. Here's a picture of a Rubik's Cube. The total number of ways that you can scramble this thing is this number here. And this is a very large number. If you were to read this, this is 43 quintillion, 242 quadrillion, 3 trillion, 274 billion, 489,856,000, and it's large. I mean, most people wouldn't actually state the exact number. They might just say it's 43 and write quintillion after it, which is a 4 and a 3 followed by 18 zeros. So this thing right here, very large number, takes a long time to write, but here we have 18 zeros in a row. You could instead say, well, all this stuff right here, why don't we just call that 10 to the power of 18? That would then get multiplied by 43. And, well, this is a shorter way to write the same number here, the approximate number of ways that you can scramble this Rubik's Cube. So that is a large number. A very small number might be something like the radius of an electron, which is a whole bunch of zeros followed by a 1 meters long. And just to put this number in perspective, a sheet of paper is about this many meters thick. So the radius of an electron is much smaller than the thickness of a sheet of paper. Now, it is possible to write this as 1 times 10 to a power, so it looks something like this, 1 times 10 to some number. And the benefit to doing this is this exponent can indicate how many times the decimal point moved. And this is more convenient than trying to count the number of zeros that appear in this number. At the end of the lesson, we'll go over how to do this, but first we need to discuss a few exponent rules. The first exponent rule that we'll look at is for multiplication. That is, if the base is the same, but perhaps your exponents are different, how can you combine these into a single exponent? We'll use example 1 to figure out what this rule is. So let's start with this one here. What is 3 to the 4th times 3 squared? It's true that 3 to the 4th is 81 and 3 squared is 9, but I'm going to take a different approach here. I'm going to write out 3 to the 4th using exponents. This means write 3 in a row 4 times. 3 squared means write 3 twice. So 3 to the 4th times 3 squared is really 3 times 3 times 3 times 3. That's 3 to the 4th. And then 3 squared is times 3 times 3. So this first part was 3 to the 4th, and the second part was 3 squared. The observation to make is, if you do this, you have 4 and then 2 more 3's for a total of 6 3's. This is the same thing as 3 to the power of 6, because there are 6 3's in a row. So this kind of shows you how you can go from this very first step to this very last step immediately. The exponents tell you how many times to write the number in a row, and at the end you just add all of those up. So you really could go from here to here by thinking about it as, oh, well, this is 3 to the power of 4 plus 2. Ultimately, what we're doing is just adding how many times we put this number in a row, which is 6. This same idea will work for 7 to the 9th times 7 to the 8th. It looks like the answers should be 7 to the 17th power if you just add up the exponents. But just to be careful, 7 to the ninth is 9 sevens in a row. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and those are all being multiplied together. And then 7 to the eighth, that's 8 sevens in a row. So 1, 2, 3, 4, 5, 6, 7, 8. And if we count these up, there's 9, then there are 8. That's a total of 17 sevens, which is this. And where did that 17 come from? That was 9 plus 8. So really, again, you can just go from beginning to the end by adding those two exponents together. And the rationale is this many sevens is 7 to the 9. And this many sevens is 7 to the 8. At this point, I think we can state this rule. If the base is the same, you can simply add the two exponents together to get your answer. This is b to the n plus m. So now that we've stated this rule, for this last part, what is 5 cubed times 5 cubed? Left in exponential form, this is 5 to the 3 plus 3, which simplifies to 5 to the power of 6. The second rule that we'll consider is for division. So not if you multiply, but what if you take b to the n and divide by b to the m, potentially different exponents? Again, we'll try to justify this rule by using example 2. Let's start with this one here, 3 to the fourth divided by 3 squared. Notice the base 3 is the same. Here, 4 and 2, the exponents, though, are different. I'll start by expanding out 3 to the fourth and 3 squared. 3 to the fourth means 3 times 3 times 3 times 3. And 3 squared means 3 times 3. The question is, how do you simplify this expression? We can cancel any common factors between the numerator and the denominator. So for example, I can cancel this 3 with this 3, and I think I'll go ahead and do that. I'll cancel this with this. And then I can cancel this 3 with this 3. And so we have this cancels with that. What we have left over is the denominator is just 1, which we don't need to write, and we have 3 times 3 on the top. And in fact, that is the answer. It's 3 times 3, which is 3 squared. So starting here, we had a 4 and a 2, and then we ended up with a 2 here. Now, what does that mean? Does that mean you take 2 and divide it into 4, or does it mean you take 2 and subtract it from 4? Both would take you to the same number. So maybe just to be clear before we state what this rule is, why don't we try this one? 7 to the ninth divided by 7 to the eighth. Taking the same approach, we'll set up a fraction. In the top, I'll expand 7 to the ninth. That is 9 sevens in a row. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And they're all being multiplied. And for the denominator, 7 to the eighth, that's 8 sevens in a row. So 1, 2, 3, 4, 5, 6, 7, 8. Again, all those are multiplied. Here, let's take the same canceling approach. I can cancel this 7 with this 7, this one with this one, and so on and so on. I can keep going. And the entire denominator is just 1. I've canceled everything from it. And there's exactly 1 7 left over. And in fact, that's the answer. It's just 7, or if you'd like, 7 to the power of 1. So did we subtract or divide? We subtracted. We're subtracting because we're canceling. I think I have an idea of what this rule is. If the base is the same and you're dividing it, you end up with the same base, but you subtract the exponents. Now, what does that mean for this expression here? 5 cubed over 5 cubed. If we use this rule, this is 5 to the power of 3 minus 3, which is 5 to the power of 0. As we've stated before, as long as the base is not 0, something to the 0 power is equal to 1. Does this make sense? It does. If you look at 5 cubed over 5 cubed, that's 5 times 5 times 5 over 5 times 5 times 5. And every time that you cancel something, 1 is left over. So if you cancel those, 1 is left over. If you cancel those, 1 is left over. This thing simplifies to 1 over 1, which is simply 1. So here, Having something to the 0 power equal 1 makes sense according to this rule too. For the last rule, we'll look at what happens if you have a negative in the exponent. To describe this rule, we'll use example 4. And let's start with this one here, 3 squared over 3 to the 4th. What we'll do is we'll examine this problem in 2 different ways. First, I want to use the rule that we had on the previous slide, where if you're dividing and the base is the same, what do you do to the exponents? If you use that rule, this is 3 to the power of 2 minus 4. It's the top number minus the bottom number. And if you simplify this exponent, 2 minus 4 is a negative number. In fact, it's negative 2. And hey, this is exactly what I want up here. We have a negative exponent. What this also means is, if you go back to the original problem, 3 squared over 3 to the 4th, and you try expanding this out, in the top that means 3 times 3, and in the bottom it means 3 times 3 times 3 times 3. If you cancel, I can cancel this 3 with this 3, a 1 is left over. I can cancel this 3 with this 3, a 1 is left over. And this whole fraction becomes 1 over 3 times 3, which is 3 squared. There are exactly 2 left over. These 2 things should be equal. That is, 3 to the negative 2 should be 1 over 3 squared. Those 2 things have to be the same. In fact, this is what a negative exponent means. If you encounter a negative exponent, it means you canceled common factors, but they're not left over in the numerator, they're actually in the denominator. So negative 2 here means the 3 isn't in the top, it means the 3 squared is in the bottom. This will work for any number that you have that is negative. For this reason, the rule for b to the negative n power is 1 over b to the positive n. Essentially, you're saying this isn't in the numerator, it in fact is in the denominator. So all the same logic will still work here as well. If you have 7 to the 8 divided by 7 to the power of 9. First, using the rule on the previous slide, this is 7 to the 8 minus 9, which is 7 to the negative 1. This is the same thing as saying if you have 7 to the 8 over 7 to the 9, here you have 1, 2, 3, 4, 5, 6, 7, 8. 8 sevens in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them in a row on the bottom. You can cancel all but 1. So this and this, this and this, this and this, all of these cancel, and exactly 1 is left over in the denominator, and we have 1 over 7 to the first. These 2 things must be equal. That means if you see 7 to the negative 1, the 7 is left over, but is in the denominator. So it is this. Now that we have this rule, if you see 5 to the negative 4, what does this mean? It means 1 over 5 to the power of positive 4. Or if you have 8 to the negative 3, this is 1 over 8 cubed, and so on, and so on, and so on. In example 5, let's use these rules to simplify these expressions. So not justify them again, but just simply apply them. Here in part A, what is a to the 12th times a to the 27th power? Since we're multiplying 2 numbers with the same base, the base remains the same, and we add the 2 exponents. And 12 plus 27 is 39. Now the directions here say to write your answer in exponential form with a positive exponent. Well, this number is positive, and we're leaving it written as an exponent instead of multiplying it out. So that is what we're looking for here. For part B, okay, now here we're dividing. We have an exponent of 31 and an exponent of 27. The base on the top and bottom are the same. Therefore, this is 5 to the 31 minus 27. And this means we have 5 to the 4 left over. 4 is a positive integer. This is an exponential form, so that's the answer. Now for this last part here, the base is 19, it's the same. We're multiplying, and here I have negative 5 and positive 2. There's more than one approach you can take to solve this problem. However, it doesn't matter that this is a negative 5. You can actually add these 2 exponents together. That is, this is equal to 19 to the negative 5 plus 2. So this is 19 to the power of negative 5 plus 2 is negative 3. This is an exponential form. However, I want to make sure the exponent is positive. This is negative. If we encounter a negative exponent, you can write this as 1 divided by 19 to the positive 3. Okay, now on to our application of exponents. Let's talk about scientific notation. By definition, a number is in scientific notation if it is of the form a times 10 to the power of n. Here, n is any integer. It could be 0, positive, or negative. And the number a is between 1, it could equal 1, but it has to be less than 10. So a couple of examples of things that are in scientific notation would be something like 2 times 10 cubed. Here, 2 is definitely between 1 and 10. 3 is an integer. You could also have, how about 4 times 10 to the negative 2? So here, this is an integer, it's negative, but 4 is between 1 and 10. I want to expand these out. This means take 2 and multiply by 10 cubed, which is 1,000. You're multiplying 2 by 10 3 times. One way to think about this is there's a decimal point here on the number 2. This number should become bigger if you multiply it by 10. In fact, it's going to move the decimal point 3 times, putting zeros after each move. Therefore, 2 times 10 to the power of 3 is 2 followed by 1, 2, 3 zeros, because we are moving the decimal point 1, 2, 3 times. This is how you can write 2,000 in scientific notation. This same logic of moving the decimal point applies even if you have a negative exponent. So here, 4 times 10 to the power of negative 2. There is a decimal point here after the 4. Since you're dividing by 10, remember a negative exponent means 10's actually in a denominator. You're dividing by 10 twice. This means this number becomes smaller, and so the decimal point goes to the left a total of 2 times. So 1, 2. And for each time it moves and there's no digit there, we can replace it with a 0. Therefore, this number is equivalent to 0.04. The decimal point started here and moved 1, 2 places. So these two are equivalent, and these two are equivalent. This is scientific notation, and we call this decimal form. Let's now look at two numbers that are not in scientific notation. Let's go back to, I think, an example I had on the very first slide. It was 43 times 10 to the power of 18. This is not in scientific notation. Now, why is that the case? I mean, it looks like it's of this form. The issue is the 43. The number a that goes here has to be between 1 and 10, and 43 is actually greater than 10. So this is a problem. If the number here is 10 or greater than 10, it's technically not in scientific notation. This number must be between 1 and 10. It can equal 1, but it can't equal 10. Another example of something that is not in scientific notation would be 0.7 times 10 to the power of negative 8. For the very same reason, the issue is this 0.7. 0.7 is less than 1, and we want this number to be either equal to 1 or greater than 1, and it's not. Okay, with this definition in mind, in example 6, let's take these two numbers and write them in decimal notation. So not like this, but like this. Starting with 3.4 times 10 to the power of 3, this is in scientific notation. 3 is an integer, and 3.4 is definitely between 1 and 10. This means multiply this number by 10 3 times. But as we discussed here, that's the same thing as saying take the decimal point and move it 3 places to the right. If you're multiplying by 10, the number must be getting bigger, and that's the direction the decimal point must move for that to happen. So I'll start by saying, well, we have 3.4, but it's being moved a total of 1, 2, 3 times. That means we have to put a 0 here and here. that means the final answer is really 3,400. So this number is the same as this one. And what about 5 times 10 to the negative 4 power? Again, this is in scientific notation. Negative 4 is an integer, and 5 is between 1 and 10. So there is a decimal point after the 5, like this. And if you are really dividing by 10 4 times, that means the number is getting smaller, and so you're going to the left 4 times. I'll be a little bit more careful with this one. This is 5.0 if you'd like, divided by 10 to the power of 4. Again, from one of our exponent rules, a negative exponent means we're really dividing by that number, not multiplying by it. So it is for this reason that this decimal point is moving a total of 4 times to the left to make this number smaller. So that is 0.0005. So here I moved it 1, 2, 3, 4 times. The number of zeros will be 1 less than the number that appears here as positive 4. So 1, 2, 3, 4 times. And that is the answer for example 6. In example 7, we'll go in the other direction now. We're going to take these numbers and put them into scientific notation. That means we want to write them as a times 10 to the power of n, and n is an integer, and importantly, a must be between 0 and 10, not equal to 10. So starting with this one here, we can think about this by actually moving the decimal point. And we want to move the decimal point so we end up with a number that's between 1 and 10. For this reason, we don't want to move the decimal point all the way to the end, because the number will be 45, and 45 is greater than 10. Also, you don't want to put the decimal point right before this 4, because that number is less than 1. So we're moving this thing until we get to the spot between 4 and 5. How many times does it move? 1, 2, 3, 4, 5, 6 times. There's 5 zeros, and we have to go one more time. So this answer is, it's got to be 4.5 times 10 to the power of, we move the decimal point 6 times. Is it positive 6 or is it negative 6? The answer is, it is negative 6, and that's because we're going to a smaller number. Okay, now same idea for part B. This is 21 million. The decimal point, I don't want to put it after this 1 because 21 is bigger than 10. I don't want to put it after the 2 because that number is less than 1. The decimal point is starting here, and it has to end up between the 2 and the 1. So to start with, I know this is going to be 2.1 times 10, and now I just have to figure out, well, what's the exponent? The decimal point, which I'll put it in here, it starts here and moves a total of 1, 2, 3, 4, 5, 6, 7 times. So it has to be 7. So is it positive or negative 7? It's positive 7 because we're making this number bigger by multiplying, not dividing by 10. In part C, well, this number kind of looks like it's in scientific notation, but the issue is this 15. It really shouldn't be 15. It should be 1.5. So for this question, I'll put a little scratch work down here. The number that should be here is really 1.5. And 1.5 and 15 are different numbers. What can you do to 1.5 in terms of multiplying or dividing by 10 so it's equal to 15? And the answer to that is, if you take 1.5 and multiply it by 10, it's 15. 15 is the same thing as this. This gives us a nice strategy for figuring out what this number should be equal to. I'm going to write this step again, but I'll replace 15 with this whole thing here. That is, this number, whatever it is equal to 1.5 times 10, and then times 10 to the 5th. So I swapped out 15 with this whole thing. Just put it right in its place. The 1.5 is good. The part of this definition that is not good is I have a 10 and then a 10 to the 5th. I'd like to condense this down to a single 10. Now, what might that be? Well, I can, if I look at these two values, the base is the same, so I can combine these into a single exponent. There's really a 1 here. I'm going to go ahead and write in 10 to the 1st. So what does this become? I'll leave the 1.5 alone. I'll multiply. Here, 10 to the first and 10 to the fifth is 10 to the 1 plus 5. We can add the exponents because the bases are the same. So that's 1.5 times 10 to the 1 plus 5, where I simply added the 1 and the 5. 1 plus 5 is 6. And so here we have our answer in scientific notation. Now, part D is also not in scientific notation, and that's because this 0.2 is less than 1. So we can do a similar trick by doing some scratch work first to then figure out what this number should be equal to. So I don't want this to be 0.2. I want it to be just 2. 2 is between 1 and 10. So what can you do to 2 if you want it to equal 0.2? Will you multiply by 10, divide by 10? What do you do? In fact, you would divide it by 10. If you take 2 and divide by 10, it's 0.2. What I'll do now is replace 0.2 with this fraction. So I'll say, okay, this thing is equal to 2 over 10 times 10 to the power of 6. And here there's a 1 here. Now, the 2 is good, but I don't want a 10 in the denominator. I want a single 10 to one exponent. This 10 can be divided into this 10 to the power of 6 over here. This is one fraction. I think I'll write it as 2 times 10 to the 6, all divided by 10 to the first. So you can divide this 10 to the first number, the entire numerator, or maybe better yet, just divide the 10 to the final part over here. So this is also equal to 2 times 10 to the 6 over 10 to the first. Doesn't matter where we divide that 10. Now, what is 10 to the 6 divided by 10 to the first? The bases are the same. Here I have a 6 and a 1. I will subtract those exponents. I'll continue that work over here. This is 2 times 10 to the 6 minus 1. 6 minus 1 is 5, so 2 times 10 to the fifth is the final answer. In example 8, I want to perform the indicated operation in parts A and B, and then write the answer, the final answer, in scientific notation. So in part A, we're multiplying two numbers in scientific notation, and in part B, we are dividing two numbers. So here we have 3 times 10 to the ninth times 4 times 10 to the negative fifth. Since all 4 of these parts are being multiplied together, we can really multiply them in any order. And the order I'll choose is, I'll say, well, this is really 3 times 4 times 10 to the ninth times 10 to the negative fifth. So this thing, it's 3 times 4 times 10 to the ninth times 10 to the negative fifth. Doesn't matter the order in which we multiply. I think next what I'll do is multiply the 3 and the 4. So that's equal to 12 times 10 to the ninth. And I see we have 10 to the negative fifth. Now we have a rule that says this is 1 over 10 to the positive 5, like this. So I'll choose to use that rule here. Furthermore, when I multiply these numbers together, I can really divide 10 to the fifth into 10 to the ninth. So I'll write this as, this is 12 times 10 to the ninth over 10 to the fifth. We're dividing two numbers with the same base. I can subtract the exponents. This is 12 times 10 to the 9 minus 5, and that is 12 times 10 to the fourth. Now, this is not the final answer. The final answer should be in scientific notation, and here the number 12, it's bigger than 10. What number should it be? It should be 1.2. So I think we have a little work to do here. So off to the side, if we want the number to be 1.2, what would you have to do to 1.2 to make it equal 12? We'd multiply it by 10. So 1.2 times 10, it's the same thing as 12. I'll take 12 and I'll swap it with this. So if I continue this work here, this is really 1.2 times 10 times 10 to the fourth. There's really an exponent of 1 on this 10. And here, since the bases are the same on 10, I can add the 1 and the 4, which gives me 5. This is 1.2 times 10 to the 1 plus 4, and that is 1.2 times 10 to the power of 5. And this thing here would be the completely simplified answer. Now in part B, we're dividing 6 times 10 to the fourth divided by 3 times 10 to the negative 3. What I'll do here is I'll divide the 3 into the 6 and the 10 to the negative 3 into 10 to the fourth. We can divide these two pieces and these two pieces together. So I'll write this as, this is 6 over 3 multiplied to 10 to the fourth over 10 to the negative 3, like this. Now 6 divided by 3 is 2, and we still have this 10 to the fourth over 10 to the negative 3. Now what do we do with this? Well, here the bases are the same, and that means you can subtract the two exponents. You can still subtract a number even if that number is negative, and I think that's exactly what I'll do. I'll say that this is equal to 2 times 10 to the 4 minus, and we're subtracting negative 3, so I'll put minus 3 like this. And as we've discussed, if you subtract a negative, if you see a negative, negative, that's the same thing as a positive. So this 4 minus a minus 3 is really 10 to the 4 plus 3. And since 4 plus 3 is 7, an integer, and 2 is between 1 and 10, this is the simplified final answer for part B.